Hello, and thanks for joining me for this session on securing SQL servers and containers for PASS Virtual Summit 2020. As a quick reminder before we get started, after the summit, don't forget to explore everything else that PASS has to offer, including the new PASS Pro memberships, the local groups, SQL Saturdays, the PASS Marathons, and virtual groups. Many events are online right now, and many events are 100% free to attendees. We'd love to see you at events year-round. In addition, don't forget to submit your session evaluations after each session and submit the event evaluation at the end of the conference. Session evaluations are very important to us as speakers, as well as PASS. It provides us with information from your perspective about what you would like to see, and it helps us as speakers get better at our presenting skills. My name is Leighton-Dick, and I'm the President and Principal Architect of Kingfisher Technologies. I'm a consultant with a focus in data protection, including cybersecurity. I'm also a Microsoft MVP for the data platform. If you have any questions after the session, I will be available live while this is being played. You can also get a hold of me on the social media contacts you see on this screen, as well as my email address, which will be at the end of the presentation. Today what we're going to talk about is how do we actually secure SQL Server when it is running in that container environment. This is a relatively new environment for SQL Server, enabled by the Linux editions that were made in SQL Server 2017, along with some new enhancements that we'll talk about for Kubernetes, for Docker, that came in SQL Server 2019. And there are a number of things that you need to think about when you're adding this into a containerized environment. And we'll talk about that in just a minute. Just as a quick introduction. In case somebody had not heard, which is very few of us, obviously, security really is no longer optional. It's become a basic requirement of application development in 2020. And the reason is that the statistics are absolutely astonishing when you get down to it. I put a number of statistics up here on the screen, but just to highlight some. Cyber attacks have become one of the top 5 risks out there in business as well as society today. In 2018, the official number of reported incidents of cybercrime was over 30,000. Just in 1 year alone. This tends to be going up exponentially every year. The average cost has escalated as well. A recent statistic showed that was over almost $4 million for a single breach. And that's just the average cost. Some breaches cost much, much more, especially for larger organizations. Overall, in 2019, we saw a total cost from cybercrime of over $2 trillion. And keep in mind that these are just the reported incidents. There are many that still go unreported because they don't meet the current requirements for being reported as a data breach. To a publicly traded company, the drop in share price is about 7%, over 7%. And that's a rather large drop. That's something that really gets the attention of your shareholders, your board, your senior management. In terms of more physical statistics, every day we lose about 780,000 records to hackers. That's one attack every 39 seconds. That's incredible. 71% of these breaches are financially motivated. There's a large contingent of organized crime in this. 34% of data breaches involve somebody inside the company in one way or another. Some of this is inadvertent. Some of this is intentional by somebody who had become a disgruntled employee or who is looking to make some extra money on the side. But one way or another, there is a lot of crime out there, and not all of it is coming from outside your organization by somebody malicious. Human error is also a major cause of breaches in today's society. In some studies that'll show some studies show this to be as high as 25%. And the statistic that I find the most concerning is that almost 30% of companies will experience a data breach in the next 2 years. This is incredible, and it illustrates that we have to do something different than we have in the past. If you haven't already increased your security across your network, not just at the perimeter, which is where we've traditionally focused our efforts, you need to, because times have changed, the attacks have changed, the methods have changed, and so our response now has to change as well. The best way to incorporate security into our environments is to incorporate it as early as possible and as often as possible. Don't just settle for a one-time event as a big revolution. Have this be an evolutionary change. Security should be involved in every layer of your infrastructure. As I said, not just at the perimeter, but in every layer, including your SQL servers, including your processes, including your applications, whether they be applications that are developed in-house or applications that are purchased from a vendor. You want to make sure you incorporate a few key concepts here when you are thinking about adding in your cybersecurity. Many of these are assumed by some of the new legislation, including the GDPR in Europe, including the new California regulations, including the one that was just passed this last week. One of those is security by design and default. And this means that you are considering security at the earliest stages of any sort of a software implementation. This is no longer an option. If you do not build in security by design and by default, then you run the risk of incurring fines if you are ever flagged with a GDPR violation. They assume that you are going to do this. This is not a request. It is no longer a suggestion. It is a requirement. You need to think about security at every step of the process. It's not just something that you bolt on after the fact. That's actually harder in most ways. You need to be thinking about how you're going to incorporate security in every step of your software lifecycle, from implementation to design to maintenance to retirement. It doesn't necessarily matter anymore. You need to be sure that you're using security at every step. And don't just settle for having one layer of security. When it comes to security, you want to have multiple layers. That's what we call defense in depth. Defense in depth essentially means that you have those redundant layers of security so that if an attacker breaches one layer, or for whatever reason one layer of that security does fail, then you have other layers which also cover it to back it up. It's not that much different from a bank. They have security at the front door, they have a security guard, they have security around the vault, they have cameras at the vault, they have a very thick-walled, very heavily locked vault that is almost impossible to breach. You want to be thinking about the same thing for your data environment. You also want to think about being resilient, not secure. Secure means implies that it's impossible to break through your security measures. And this is no longer possible. Hackers have gotten too good, and the environments are just too complex. Instead, think about being resilient. Think about having those multiple layers that can back each other up. Think about and make sure you have a plan for how you're going to recover quickly, how you're going to minimize the damage in case there is a breach or in case there is some sort of a failure. That is how you build a truly resilient environment that is able to be recovered quickly, not just something that is viewed to be secure and hardened. As I mentioned, you want to build security and privacy into all of your IT processes. And I'm listing on the screen here just a few of those processes. But think about it when you're evaluating. Think about it when you're designing. Change management, your DevOps processes. We'll talk more about some of these as the presentation goes forward. But the bottom line is that right now, when we are rebuilding some of these environments using containers or using some of the newer technologies, when you are adding your DevOps processes, take this as a unique opportunity to improve your security and your data privacy as well. Many of these newer platforms actually natively support the security, but you have to take the time to implement them. Most do not implement the security by default for various reasons, and we'll talk some about that as we go through this session. One argument I've heard in favor of skipping the security or putting it off until later is that it slows you down, or it makes you less agile. That's not necessarily true. If you are planning ahead, if this becomes a natural part of your software lifecycle, it does not necessarily have to slow you down. You just have to be prepared. You have to plan for it. Before I get going on the main section of the presentation, I just want to make a couple of disclaimers. First of all, this is not a comprehensive list of things that you need to do. This is a good place to start. I'm going to present a lot of things, but it will be high level. I'm not presenting code in this session, mainly because there's too many variations. It's simply not possible to cover everything on all of these platforms in 1 hour. So if this is something that becomes a concern to you, if you need to move forward with any of these, make sure to consult an expert on the platforms. The second disclaimer is that we're going to narrow the scope of the presentation a little bit. We're going to focus primarily on on-premises Linux installations. While you can run containers on Windows, the vast majority are run on Linux in one form or another. And we're going to focus on on-premises because that's where most of the security actually needs to take place. If you're using a cloud IaaS service such as Azure Kubernetes service, that type of a service will handle some of the tasks for you. Not all. No cloud service does take care of all security for you. However, it does take care of some of the most demanding requirements and some of the basic requirements that we're going to talk about. Make sure to consult whatever platform that you choose to make sure that that you know what it is that they cover and what you need to configure. The first layer of this is the host. And this is the Linux box that is running your Docker, running your containers. In order to secure that container platform, you have to make sure that all routes to it are secured. And this isn't just the host. If this host happens to be a virtual machine itself, you will need to secure the host underneath that. You'll need to make sure you secure the network. You need to make sure that you secure the storage appropriately. You need to secure every piece of it leading from the internet all the way into the entrances to this host. And one thing to keep in mind here, again, is that Linux, by default, is really not secure. Now, some of the distributions have gotten more secure in recent years. That is true. However, we're going to talk about a number of things here in which they are things that while you can secure them, they are not by default in order to make them easier to use and easier to implement. The first of those is permissions. By default, Linux is relatively open on permissions. Yes, it is more secure than a default Windows installation in a lot of ways. They do have more natural isolation in Linux. They do have the ability to have a root account that is completely separate and unused if you choose to. They have many variations on password policies available. But most of this isn't implemented by default. By default, the root account on most Linux distributions, including the ones that SQL Server is supported on, is enabled. You want to make sure that you disable root and always run as a standard user. Most of the time, you have a sudo account or a sudo command. You have a sudo command that enables you to do administrative functions using a standard user account, and this is the way that you should organize your workflow within a Linux environment. You want to make sure that you upgrade the password policy. By default, the only password policy that's installed in most Linux distributions is that you have to have a minimum of 6 characters. There's no complexity requirements. There's no expiration requirements, and you need to really increase that. You can actually create the password of password by default in Linux, which is completely insecure. That should be one of the first things you do once you install it, is to increase that password policy, increase the complexity, increase the expiration requirements on that, so that those passwords are secure for all users when they are created, and you cannot create an insecure password. A 6-character password is able to be defeated in a matter of seconds in many cases. You also want to make sure that you're locking accounts after unsuccessful logins. And this applies to development servers as well as production servers. This should be a blanket policy for all servers in your environment, really. And that prevents a brute force attack. For securing the host at the network level, most companies don't use IPv6 at this point in time. There are a few exceptions. It is starting to become adopted in some areas. However, in many cases, we're still relying on IPv4. We're still relying on the private address spaces that we're used to. However, IPv6 is, in most distributions of Linux as well as Windows, it is enabled by default. And if it's not used, then it can be used as an attack vector, because an attacker can hide his traffic if it's not on an IPv6 pathway if it's not being actively used. You want to remove the services such as telnet and FTP, rlogin, RSH if you don't use them. Again, these are methods of an attacker using an unused service to be able to sneak past your defenses. For SSH, which is commonly used as a remote access method for Linux servers, change the port. By default, SSH runs on port 22, but that's extremely well known. If you change the port, yes, it is security by obscurity, but at the same time, every little advantage that you can give yourself slows down an attacker just that much more and gives you a little bit more chance to catch them before they're actually able to do any damage. You also want to block root logins on an SSH. Like before, there's really no reason to use root on Linux. You can use sudo for pretty much anything that you need to do. And so the best thing is to just block the root logins on SSH so that you don't grant that super user permissions to somebody that is coming in from a remote system. For disk, by default, Linux installs everything on a single partition. This isn't great from a security perspective just because it allows everything to be read-write. The best idea is to set some certain critical partitions such as boot to read-only, and that limits the impact that they can have on the operating system itself if somebody does break through your defenses. For services on the Linux, you want to make sure that you are securing any network-enabled services. And the best example of this is something like Apache Tomcat. It's a very, very common web server. Just like any software, it does have some vulnerabilities. You want to make sure that you prevent somebody from accessing those services when they should not be. Remove any services not being used. And I go back to the same examples we showed before. Telnet, FTP, RSH. Anything that's not being used can be exploited. Anything that's not being used can be replaced with something else. So just shut them down, get them off, preferably uninstall them from your server to prevent them from being exploited. It's called reducing your attack surface, and it's very important. Disable services that are only used occasionally. If, for example, you use FTP once a month to be able to download something, make sure that between times that you actively use it, that you are disabling FTP so it can't be exploited. And then anytime you start disabling or removing services, revisit that list on a regular basis, because things do change. New vulnerabilities exist. Sometimes you'll change which services that you use. You may need to install some, you may need to remove some others. It's really, reducing your attack surface is extremely important. A couple other quick recommendations for the Linux host. Make sure that if you don't have some sort of firewall in your environment, most do, but if you don't have some sort of firewall, if you don't have some sort of intrusion detection service, that you do enable those on the Linux server. And then keep your audits, keep your logs, and make sure you're reviewing those on a regular basis. Make it a scheduled event. All the logs in the world do you absolutely no good if nobody looks at them. That's not something you want to keep just for an auditor. Okay, moving on. Level 2 of this environment is Docker. And since you're here at this session, I'm assuming you're at least a little bit familiar with Docker. But just for those people who are not necessarily as familiar with it, who have mainly heard the term but haven't used it at all, Docker is what's known as a container platform. And you can think of containers as ultra high density virtual machines. Because they do not require a full operating system within the container, like a virtual machine does, because they have no GUI to make it easy to administer, they are able to be much smaller, and you're able to duplicate them much more than you are with a standard virtual machine. This is an example image just from the Docker website. On the right, you have your standard virtual machines. Everything has to have its own full copy of the guest operating system. Everything has to have, everything can have all of the applications that it needs, and is very self-contained in most ways. However, there's a lot of duplication. You will have a lot of the same services, a lot of the same applications on every single virtual machine. That adds a lot of overhead, both in terms of disk resources as well as processing and memory. On the other hand, a containerized application still has the infrastructure on the bottom. It still has a host operating system, often Linux. It still has a hypervisor. In this case, the hypervisor is Docker and not something like VMware or Hyper-V. But beyond that, the Docker container is actually much, much smaller. It contains a very heavily streamlined copy of the OS inside each container, just enough to be able to run the environment. As I mentioned, there's no interactive method in there. There's no GUI. There is a shell that you can get to, but for the most part, you don't even need to use that very much. Everything is handled from outside the container. Generally, for each container generally has one application installed. It might have 2 or 3 small related applications installed, but it doesn't have any overhead, really. It's just the things that are necessary to perform a certain task. This makes it very flexible in that you can spin them up and destroy them basically at will. It also makes them able to be packed much more tightly on an individual host machine. A couple more things about containers. The container itself, is created from an immutable image. Think of this as a CD-ROM, where it's written once, it's burned permanently, and after that image cannot be changed at all. If you need to upgrade that version of the container, you simply destroy it and create a new one. If you have something like data that needs to be included in this container or used by this container, you mount that on an external volume, and that's something that you create when the container is created. It's persisted outside of the container, actually in the host operating system. And that enables you to very quickly and very easily destroy this and upgrade the container. Destroy it and replace it with a container that hasn't been corrupted in the case of a security violation. A couple of warnings on this, though, is that Docker was not originally designed to be secure. That was an afterthought. It was originally designed just for this flexibility. Because of that, there are things in the system that, such as root mode. Docker by default and in production scenarios runs as root in today's environment. They do have a rootless mode that runs with a standard user account, but that's experimental at this point. It's not recommended for production use yet. You have to be aware that it does run under those root permissions, and that means that if something does manage to run within the Docker hypervisor, that is running with the full permissions of the operating system. It's not constrained in any way. The containers, OS, and applications are also subject to the same vulnerabilities. Keep in mind, these are just the applications that you'd normally run in a Linux environment. If you choose to run SQL Server there, it's the same SQL Server. If you choose to run PHP in a container, it's the same PHP. All of these things are exactly the same, and so they will have the same vulnerabilities. They also have, as I said, a micro OS embedded in each container. This also has the same vulnerabilities as you would find outside the container. So you do have to pay attention to security when you're doing these and keep them up to date. We'll talk about how exactly to do that at the end of the presentation. Containers also have no native isolation from one another. This is something that has been starting to change just a little bit, but at this point in time, you have to assume that unless you configure it otherwise, the containers can have full visibility into each other. There are no restrictions between what the containers can do in other containers and how they can interact. So you need to make sure that you're paying attention for cross-container compromise. That's what that's called. Keep all the containers on the same host up to date. Again, this is the patching that we're going to talk about at the end of the presentation. And make sure that regardless of tier that you're following security best practices. It is just as important to secure a development environment in this type of scenario as it is to secure your production environment. And for that reason, you also want to make sure that you don't mix production and pre-production on the same host. Pre-production is often not secured quite as tightly, or at least it has to open up additional functionality in order for developers to make the changes that they need to do and do their jobs. It's also recommended with Docker not to run other services on the same host. So if it's a Docker server, have it be a Docker server, and that's the only thing that it does. I mentioned that the Docker system itself runs as root. Many containers also run as root under Docker. This is something that's slowly starting to change. SQL Server 2017 actually ran as root in Docker by default. They have since introduced a method of being able to run SQL 2017 using a non-root user. Microsoft has documentation on that. The link is on the screen. When they upgraded to SQL 2019, that does use a non-root container by default. This is changing, but at this point in time, you have to assume that unless you see otherwise, that it is running as a root and it does have full permissions of the operating system. By default, when you install Docker, any user on the system can control that Docker environment. It is not necessarily locked down. You want to make sure that you're restricting control over Docker to only trusted users. For host resources, make sure that at the Docker level, the hypervisor level, that you're securing all the files and directories used to run Docker. To prevent any changes from somebody that is not an administrator that should not be changing Docker. Again, this is a security best practice to isolate that part of the operating system from something escaping the Docker container sandbox. For the network, make sure that you are using a user-defined network. This is something that a lot of people don't do at this point in time, but the default bridge, Docker 0, because it's well known, because again, security is not installed necessarily by default in Docker, it's subject to flooding attacks, ARP spoofing, and these are things that are easily preventable by using a user-defined network in place of that Docker 0 bridge that it installs for you. For shared resources between the container and the host, one of the biggest issues is with mounted volumes, because that is a way that's expected to be used to escape the sandbox of the container, right? That's how you persist data. Make sure that for anything that you are mounting into your container, that you are properly securing that and making sure that you're locking down that directory to only those users from the container that should be modifying that data, as well as users from the host that should be able to access that data. Lock it down as much as possible to prevent something from escaping the sandbox. And by all means, only mount the directories that have to be mounted inside the container. Don't mount a sensitive directory outside into your container. And so this would be directories such as the boot partition again, such as the root directory, such as many of the other system partitions within Linux that contain the Linux operating system itself, as well as your other applications. You want to make sure that nothing can escape that sandbox any more than you specifically need it to. For a similar reason, there's what's called the Docker socket. The Docker socket allows something inside the container to actually interact with Docker and control Docker. You don't really want to mount that Docker socket inside your containers. And the reason is that, again, that allows something that's within this container to escape the sandbox and run commands on the host. And that's a very dangerous proposition. And because it could allow that Docker container to control the host in full. And likewise, don't share the host namespaces. Namespaces in Linux are a way of partitioning. It allows isolation so that, for example, something in the network partition cannot access something in the user partition and vice versa. If these are in different namespaces, then one cannot access the other. So don't use the host namespaces inside the container. Again, that prevents something from escaping that sandbox. You want to make sure that you lock down the containers themselves to prevent the containers from acquiring privileges that they shouldn't. Only allow them to run what they are designed to run. Make sure that you're removing any unnecessary capabilities or services from the container's operating system as well. And I've listed just a few of those up on the screen, but in general, anything that you don't have to use within the container, get rid of it. One that is very commonly mentioned is SSH. SSHD is the SSH daemon, which is actually what runs SSH on Linux. It's very important because if you have SSH enabled inside the container and that container is breached, then they could use that as an access point to be able to remote out to any other server in your environment and potentially breach something else. You want to eliminate those possibilities of moving from container to container or from container to host. On the container's network, only open the necessary ports. By default, again, they did not want to restrict what you can do inside the container to make it flexible. However, when you're trying to secure Docker, you want to make sure that you close any ports, block any ports that are not absolutely necessary for the operation of that container. When you're mapping ports, similarly, don't use ports below 1024. Ports below 1024 are very well known. They are frequently used to transmit sensitive data. If you remap those for Docker, then potentially you have another attack vector. For the resources within the containers, make sure that you're restricting memory and CPU. And this is something you need to pay attention to as far as each different application. What does that application actually need? What does it require in order to be able to run? So you're looking not only for your minimum system requirements, which is we frequently look at. If something requires 4 processors, you don't want to give it 1. But if something only requires 4 processors to run well, only give it 4 processors. That makes it much more obvious if something is something additional has been added to the container, or it's running some code that it shouldn't be. It also prevents it from gaining too many resources on the server and being able to run a lot of processes it shouldn't be. A classic example of this is crypto mining, where they install software in a hidden location in your system to be able to mine cryptocurrency like Bitcoin. Crypto mining is something that is done that takes a lot of resources, a lot of CPU. If you restrict that CPU to 4 processors or 4 cores, and it suddenly spikes that up to 100%, there's no room for it to be able to escape attention. Likewise, you want to set the root system to file system to read only within the container, similar to what you did at the host level, and limit the number of allowed process IDs. Again, this locks it down so that it's much less likely that that container will be able to be used for things other than what you intended. Make sure that any secrets such as passwords that are used in connection strings are stored outside of your container in dedicated management tools. You can put secrets directly into your Docker file that's used to spin up your container. You can put it directly on the command line when you start your container. Try to avoid this. Put it into that dedicated secrets tool. This is kind of like an EKM device or Azure Key Vault. There's other similar systems in that it stores it in encrypted fashion outside of any way for that attacker to be able to view that information easily. Make sure that when you're spinning up container images that you're scanning them for vulnerabilities. This is extremely important because, as I mentioned before, there are a number of vulnerabilities out there that will end up in your containers if you're not paying attention. It's software. They slip in. Use a tool, and there are a number of them out there. Use a tool which can scan those container images for vulnerabilities and log that to make sure that it's known that these are clean when they're installed. And then use what's called Docker Content Trust if you're able to. This is basically code signing for all of the code in the repositories, which are the places that you get new Docker containers, Docker images. Finally, for Docker, just like everything else, make sure that you have logging enabled, and make sure that you're regularly reviewing those logs for any potential issues. Level 3 of this is securing Kubernetes. Kubernetes is a much newer concept to many of us than Docker is. It's something that I'm still learning a lot about, honestly. It's really been adopted heavily by Microsoft in the last year or so, at least publicly. It's what you would call an orchestration layer. It runs on top of Docker to allow that Docker environment now to be scaled automatically and to maintain certain characteristics as you move forward. This automates a lot of things. It makes it a very, very flexible environment, able to run a lot of containers across a number of hosts, not just a single host, to be able to really give you the scale that you're looking for with containers and allow it to be able to handle a number of situations and be able to spin itself up and down in order to handle the load. Kubernetes is really focused on that scale and the automation. That's what it was designed to do. That's what it's best at. It was actually designed by Google back about 6 years ago, and that's where all of this idea of scale came from. Google will automatically scale to a huge extent in their own environment. This extends that out and allows you to run it in your environment now as well. It's now open source. It's maintained by the Cloud Native Computing Foundation. So Microsoft was able to adopt it. A number of other people have been able to adopt it. There's a number of implementations out there. Because it runs top of containers, it's obviously not required for containers, but because it adds so many benefits to a container environment, it is becoming increasingly common. For those that aren't familiar, this is kind of what a Kubernetes environment looks like. You have the master or control plane up there at the top, which contains all of the core functionality which coordinates the activities of all of the nodes, all of the places that the containers are actually running. And then down below, we'll talk about this more in just a moment, but you have the nodes. The nodes contain pods. There's plugins which allow coordination among all of the nodes. It's a very complex environment, but it's also extremely flexible and gives you a lot of power to be able to handle all of these containers at scale. A few definitions just before we go forward, just so everybody's on the same page. The control plane, as I mentioned, is the main controlling unit of a Kubernetes cluster. It manages the workload. It manages communication among the nodes. It contains a number of processes itself, including the process called etcd that stores the configuration data. It contains the API server, which allows you to interact with it. The scheduler, the controller manager, all of these things are within that control plane or master node. Below that, you have the individual nodes. A node is simply a machine where containers are deployed. Typically in Kubernetes, you will not have just one node. You will have a number of different nodes. That's where the scale comes in, and that's where the power really comes in for Kubernetes. Within each node, you have one or more pods. A pod is the basic scheduling unit in Kubernetes. It contains one or more containers, the pods all share, the pod contains resources that are allocated to all of the containers that are within that pod. Pod also provides a basic level of isolation in that a container within one pod cannot, by default, contact a container in another pod. It must go through the pod architecture and the Kubernetes architecture in order to be able to reach the container in the other node. Pods can also be shifted between nodes, or they can actually be spun down in one and spun up in another, is probably a more accurate way to say it. This allows Kubernetes to rebalance the load as necessary in order to maintain performance and in order to maintain some of the restrictions that we'll talk about later. You have a replica set, which is a grouping mechanism. You have a service that is a set of pods that work together, that itself is assigned an IP address. That's the primary way that you interact with pods in order to, again, abstract away the pods from the actual, from the what you're actually trying to do with those pods. You have namespaces like you do in Linux. You have labels that can be attached to any API object, such as pods or nodes, which allow you to, again, dynamically control which ones are being used and how you refer to them. You have selectors, which is basically a query into the environment. So you can query both by the labels as well as attributes or fields of each individual pod or each individual object. Both the labels and the selectors provide a lot of dynamic capabilities. And then the last term I'm going to give you is a kubelet. Kubelet is a component in a node. It's basically the controller for that node. It understands the running state of the node, what's running in the node, and it also watches to make sure the container is healthy. Kubernetes has a lot of power when it comes to security. You're able to do a lot of things with it. However, most of it is not enabled by default, just like what we've been talking about with Linux and Docker. Out of the box, it's going to assume that all pods should be able to talk to all other pods. It is not in any way secure by default. Its values scale first. You have to go in and you have to secure all this stuff. It is very securable, but you have to do it. And for this reason, just like with Docker, make sure that you're using different Kubernetes clusters for production and pre-production whenever possible to provide that isolation. Make sure that the more porous environment for development and quality assurance cannot get to your production data. So I've got a number of things here listed on the slides to discuss for securing Kubernetes. I'm going to cover these at a relatively high level. But make sure that you're, just as one example for permissions, make sure that you're using role-based access control. It's just like in Azure, you have the ability to control all of the permissions by a customizable role, where you are assigning permissions to that role and then you assign users to the permissions. This provides a lot of flexibility, and Kubernetes, we'll talk about this over and over, but flexibility is everything. You don't want to hamstring the ability of your Kubernetes cluster to be able to react to the conditions that you're setting aside for it by hard coding essentially these permissions or these policies or these capabilities into the definition for a specific pod whenever possible. You want to use these policies as high-level things that can be applied dynamically to allow as much flexibility as possible. When you're using the role-based access control, try to avoid duplicating permissions. You can assign multiple roles. Approach it that way. And avoid granting cluster admin privileges any more than necessary. Again, you want to run with the lowest level of permissions possible, just like we talked about for the hosts and for Docker. Kubernetes has the concept of policies built into it, in which you can just define some general rules about how something should be run, and then that's applied again dynamically, in an automated fashion across the environment. Use that whenever possible. Avoid the manual or one-off approaches like I talked about. In addition to hamstringing the flexibility of Kubernetes, you're also introducing the possibility of drift, where things change a little bit over time, and that can fly under the radar a little bit. A couple examples of the way that you can secure Kubernetes with policies are you have network policies, which specifies how a pod is allowed to communicate with other entities on the network. And an entity can be a pod, it can be another service, so on. And this is how you would handle some of those situations I mentioned a couple of slides ago. Resource quotas. You want to reduce the resource consumption per namespace. So this could be like quantity of objects that are allowed, the total amount of CPU or memory that could be consumed by a given pod or a given resource, and so on. You also have something called an admission controller. An admission controller is another type of cluster level object, which can be implemented. It's not by default, but it can be implemented to govern and enforce how the cluster is used. For example, it will allow security policies to be created, and they are implemented within the admission controller. You can block images from untrusted repositories from being run on your Kubernetes cluster. You can even fix misconfigurations on the fly to some extent. You can enforce your resource limits. Another way you can do that. You can even control what types or what tags can be used by a cluster. So for example, if you want to make sure that you're always running a known version of a container, you can prevent the use of the latest tag, which is very common for within Docker containers to indicate just use whatever the most recent version is. If you need to make sure you're using a known version, you can prevent the use of the latest tag within Kubernetes so that you have to use a tagged version. I mentioned the pod security policy. Some examples of what you can do with this is preventing a container from being run as root, blocking one of those holes that I mentioned for Docker. You can prevent it from using host resources. You can prevent it from having a root file system that is not read-only. All of these things that we talked about as vulnerabilities within Docker, you can partially prevent using Kubernetes if that is the only way you're running your Docker containers. For securing Kubernetes for isolation, again, you have the namespaces. You have what's called taints and tolerances. A taint is a property of a pod that allows a node to repel a set of pods. So whereas affinity is saying always make sure that pod A runs with pod B, a taint is the opposite. Never run pod A and pod B at the same time, or within the same pod, or within the same node. You also have a toleration, which kind of overrides a taint or suggests ways that taints can be overcome. You also want to make sure you're limiting resources, just like you do with Docker, restricting CPUs and memory allocated to each pod. Just like in Docker, this prevents a pod from being used for something you don't intend. Limit unnecessary access to the API. Make sure that the client connections are using TLS, using etcd. Within the kubelet, make sure that it is being run as a known user to prevent that from running again. Something like a cryptocurrency miner, some sort of network attack software, backdoor software, what have you. And then secure the ports that the kubelet also uses. It has a couple that it uses by default, and you can just make sure that that those can't be accessed by anything but the kubelet. Just like with Docker, you want to make sure that you're encrypting all secrets. And it does have built-in methods in order to be able to do this, or there's also plugins that you can get in order to be able to do this. And then logs and audits. Just like before, monitor your network traffic, make sure that you're reviewing your logs, look for things in your logs like anomalies, know what it's supposed to look like for your Kubernetes installation. Look for API calls that shouldn't be happening. Again, know your baseline. And then watch for authorization failures, which are marked in a Kubernetes log as forbidden. Finally, we get to SQL Server. SQL Server within the container really is just like SQL Server anywhere else. It is, remember from talking about SQL Server on Linux, that it is the same exact code that is being run in Windows, in Linux, as well as in your container. It's the same exact SQL Server. And so therefore it's going to react exactly the same way. Your methods of authentication are the same. You'll want to set up your securables and permissions the same way you would for on-premises SQL. You want to use certificates the same way, and so on. It's just SQL Server. A lot of the same rules apply. Most of the hard work when it comes to securing SQL Server in a container happens underneath that in Kubernetes, in Docker, and on the host. And that's great news for us as DBAs. But a few things just to remind you of when you are talking about this. because of the way that Kubernetes and Docker are frequently used, because of the way your containers are frequently used. One very common use is to be able to quickly spin up pre-production databases for developers or for testing. Make sure that you're never directly copying production data to pre-production. That's a general best practice anymore. You want to anonymize or mask the data, and there's a number of tools out there to do that. Change your passwords into a pre-production environment, and enforce password requirements whenever possible. And then it's always a good idea to encrypt connections to any SQL Server, regardless of whether that's running on the host itself or whether that's running within the container. TLS is supported, and that is the recommended way to secure that connection into your SQL Server container, is by using that native capability of SQL Server to have an encrypted connection directly into it. You can still use a VPN or an IPsec connection, just like in a for standard SQL Server. But by using TLS, you're getting that encryption all the way into the inside of the container, and that's really the most secure way to do this. Okay. One of the last topics I want to talk about very briefly is patching. And this is really fairly simple and straightforward. With Ubuntu Linux, and depending on the distribution of Linux that you're using, there's different commands that you use to patch your Linux host. For Ubuntu, there are 2 different package managers available. apt-get is an older one. It's one that's available pretty much universally in many Debian-based distributions, of which Ubuntu is one. But the preferred one is a newer version of apt-get called just apt. There are some minor differences between the two as far as the way that you interact with it. But for the most part, they adopted much of the same syntax for apt as for apt-get. So in order to refresh the list of packages that are available from the repository, which is the place that you get your software updates. It's kind of like the App Store. You will always use the sudo command because you want to run this as an administrator in many cases in Linux. So it's either sudo apt update or sudo apt-get update, and that just goes down. It downloads the list of currently available packages of it from the repository. In order to actually implement the upgrade and get the latest version installed on your system, you say sudo apt upgrade. Upgrade by itself will install anything new, but it does not remove any of the libraries that are no longer used by the current versions. If you want to do that and kind of clean up when you are installing the packages, then you will say sudo apt full upgrade, or if you're using apt-get, you'll say dist upgrade. And this actually makes your local copy of your system exactly match what's on the repository. Gets rid of all the stuff that you're no longer using. However, the reason they don't do this by default is that, just like in Windows, this can break things when you're removing software. Finally, if you need to do a major version upgrade within Ubuntu, you say do release upgrade. And that actually will go out and will grab the latest version of Ubuntu. So this is when you're changing major versions. For point releases, those minor changes, minor hotfixes, upgrade will take care of that. This is like go from 14 to 16. Patching Docker and Kubernetes on the Linux platform is very, very simple and straightforward. That's handled by the upgrade command, just like any other package on your system, because that Docker and Kubernetes both are packages on your system. And it's extremely important in this environment because they are so powerful to keep up to date with all of your security patches for both of these. Upgrade Docker, upgrade Kubernetes frequently. And then patching SQL Server and any other containers that you use in this environment. You go out, you download the newest image from the repository, from Docker Hub, and then you destroy the container and recreate it. Again, your data should be outside in mounted volume. That should be recreated. If for whatever reason that you are instantiating your containers using the command line, you want to make sure that you save that command in order to be able to reuse it each time you need to update. If you are, but the better way is to create what's called a Docker file, which is just a script that creates the container. And then when you have the Docker file, then you can just instantiate this with the exact same settings each and every time. And again, Kubernetes will help you with this. Finally, for DevOps, keep in mind that you must secure your DevOps pipelines or all of this breaks down. A lot of the reason that we're adopting containers and adopting Kubernetes is in order for this automation to take place and allow that the software that we're developing can flow through in a smooth process, a very automated, simple, straightforward, repeatable process from all the way from development through all this testing that we now want to do and get it into production with as little resistance as possible and in as predictable a manner as possible. This sort of a pipeline concept is intended to introduce change which makes it inherently vulnerable. So make sure that you are paying attention to what goes through your pipeline. Adopt the tight security practices, including in your development environments. It's absolutely critical in DevOps to make sure that you're adopting those practices and make sure that you are secure the entire way through. Add in that automated security scanning, multiple layers of it preferably for different types of vulnerabilities. This can include container scanning as well as things like static code analysis as well as your unit tests and such. To wrap it up, security is absolutely critical, regardless of what platform you're running on. This can be on-premises, that can be in the cloud, this can be a full version of SQL Server, it can be a managed instance, it can be a container. Make sure that regardless of where you're developing your code, regardless of what databases you're using, build in security from the start. We covered a lot of tactical pieces in this presentation about how to do that with a container, but make sure you're always using it. Think secure, think resilient. Thank you very much for your time today. I appreciate it. Don't hesitate to contact me if you have any more questions. At this point, I'll stop the presentation and we can cover any more questions that you have with the remaining time. Thank you very much and have a great summit.